next speaker. Our next speaker is Colin from UCSD. Colin is currently a PhD student in computer science program at Stanford, after having received his bachelor's and master's in computer science from UCSD. His work has primarily focused on hardware security, particularly emergent side channels in FPGA environments. Colin works with the Kastner research group with Professor Ryan Kastner and collaborates with members of industry and other universities. Colin.
Now? Thank you. You're very helpful over there. My name is Colin. I'm a PhD student at Stanford University. This is a project I worked on as an undergraduate student, master's student at the University of California, San Diego, where I had the privilege of working with this team of wonderful researchers. Field programmable gate arrays strike an alluring balance between computational efficiency and reconfigurability, but oftentimes they remain prohibitively expensive to both own and to develop applications for. What this has increasingly pushed us towards is, first, cloud FPGA leasing schemes, or what I'll call temporal sharing, where you lease an entire FPGA device from a cloud provider, perform your computation, and when you're done with your computation, you relinquish the device back to the cloud service provider. It's also pushed us towards the integration of proprietary IP. So to cut down on development and verification time, you can lease some proprietary IP core that's potentially encrypted, integrate it into your design, and save significant amounts of time. And more speculatively, it's led us to consider full FPGA virtualization, or what I'll call temporal spatial sharing, where not only are there multiple users on the same FPGA throughout time, there are multiple simultaneous users on the same FPGA at the same time. But what we observe is that these are all multi-actor structures. And what I mean by that is there are potentially hidden opaque circuits running alongside you on the same FPGA device. And this is immediately clear when we consider temporal spatial shared cloud FPGAs or multi-tenant FPGAs, where you, the user's logic, is alongside potentially n other users' logic at the same time. We have to be careful here because while there are logical boundaries in place, all of the actors on these systems share the same power system. And so if a dedicated attacker were able to instantiate a voltage fluctuation sensor within their region of the allocated logic, they could potentially determine what core other actors are executing on the same FPGA. If it's a soft processor, they could determine what's running on that soft processor. Even more damning things, they could perform a correlation power analysis attack and extract a cryptographic key, or even more specific things like they could detect round 7 of AES computation to know when to induce a power fault for performing a DPA attack. Now we're going to focus around temporal spatial or multi-tenant cloud FPGAs, and that's what we're going to refine our threat model around, but we're studying fundamental qualities of voltage fluctuation sensors that's going to apply to any of those three multi-actor structures. So in a multi-tenant FPGA threat model, we have some device, a multi-tenant FPGA, located in a data center somewhere. On that device, some user is running some confidential computation. And at a remote location, an attacker wants to access the device and extract some information from this user running a confidential computation. And to do that, they're going to co-locate with that user on the multi-tenant FPGA and deploy one of these voltage fluctuation sensors. They're then going to collect some sensor readings. Then they're going to optimize theta and phi based on those readings. And theta and phi are two optimization parameters of the type of voltage fluctuation sensor that we discuss. Then the attacker is going to extract data from the sensor and derive some confidential information from it. Determine what's running alongside them on the multi-tenant FPGA. If it's a cryptographic core, determine what key that cryptographic core is using. Now, I've discussed voltage fluctuation sensors fairly generally so far, but we're primarily interested in time to digital converters. At a high level, this is an instrument for synchronously measuring the load on the power distribution network. I'll note briefly that it's easy to disguise, as they just resemble carry adders, and they can be designed to include no timing violation, so it's fairly trivial to upload them to existing cloud infrastructures. I'll give a very brief overview of what a canonical TDC looks like so that you can understand how we augment it in our work. You begin with an array of elements that have some uniform delay, and you lay out those elements linearly on the FPGA. You then instantiate a clock generator that sends rising and falling pulses that propagate through this long array of delay elements. You then instantiate a second clock that is phase offset from that first clock, a constant amount. And this second clock is going to clock a set of registers, and those registers are connected to the output of those delay elements. And if you pick a constant phase offset such that the signal generated by this launch clock does not propagate all the way through the delay elements, that signal will be captured somewhere in the middle of this long array of delay elements. And it turns out that the distance with which this signal propagates is a function of the state of the power distribution network. And as a result, we can measure the instantaneous load on the power distribution network. Now, there are some known problems with this design. While I presented a nice academic theoretical model, this idealized perfect delay line doesn't really exist. We eventually need to map this time digital converter down to actual FPGA primitives. But we want to get the most linear propagation we can. We want a primitive that has very linear propagation because that will make our power fluctuation sensor more responsive to changes in the power distribution network. We also want our delay elements to be very fast because the faster they are, the higher resolution our power sensor will be. And what we end up doing is mapping our time to digital converter down to the carry chain primitives of the FPGA device. Usually these carry chain primitives are 4 or 8 bits wide, and they're used for constructing carry adder for addition operations. And the advantage of them is that they are fast and fairly linear, but only locally. Only within that 4 or 8 bit width of the carry adder element can you expect them to be fast and linear. And so our time digital converter looks more like this, where we have to compose a number of these carry primitives together to form the entirety of that long array of delay elements. And so what we'd expect, theoretically, is that as we change the phase offset between that launch and the capture clock, thus allowing the signal to propagate further and further through the array of delay elements, that we would see very fast and very linear propagation within a single carry primitive, but then the transition would plateau as it crosses into the next primitive. And our physical data bears this out. We see 4 bits of linearity when we test this on pink 7 series devices, which uses a carry 4 structure. So there are 4 bits of linearity where we see a very responsive sensor behavior, and then the signal plateaus for a period of time before it enters the next carry element. And we see 8 bits of linearity on AWS, which is an ultra-scale plus part, where propagation is very fast and again, very linear within those elements, and then plateaus between the respective carry elements. Our solution to this is to use dynamic theta tuning. So when I introduced this sensor, I said we use a constant offset between the launch and the capture clock. But if we instead replace that constant offset with a programmable clock generator, we can then configure exactly how far the signal propagates through our array of delay elements. It's now configurable. What that means is an attacker can place the transition at an ideal point within a single one of these carry primitives, and thus improve the sensor's response to power fluctuations. You can place the signal such that it doesn't fall on one of those plateaus we saw in the stair stepping earlier. Now I'll move on to a new problem that we address in our work. Regardless of whether you're using a constant phase offset, or what we call theta, or you're using a dynamically tunable one as we do in our work, theta, which is again the phase relationship between when we launch that signal through the delay elements and when we capture its propagation distance, theta defines a window. And only power fluctuations that happen within this window are capable of being captured by the time to digital converter. And it's important to note that the victim core that we're trying to extract some data from is also likely synchronous. And it's also likely that the power fluctuations that this victim core induces are going to be very brief and very centralized around the positive edge of the victim core's clock. Now, right at the positive edge of the victim core's clock, it's going to trigger most of the registers in the design, which is going to induce the largest load on the power distribution network. But for the rest of the victim clock's period, the power distribution network state is going to be fairly nominal. So we can end up in a situation like this, where that synchronous window of sampling, whose width is defined by theta, that synchronous sampling can be out of phase with the victim clock, such that we're just synchronously sampling on the nominal state of the power distribution network and missing a significant amount of information about the victim computation. What we really need to be able to do is phase shift the launch and the capture clock together such that this synchronous window of sampling synchronously aligns with when the victim computation is inducing potentially sensitive information onto the power distribution network. And so that's what we'll do. We'll phase shift the launch and the capture clock together with respect to some victim computations clock. And so we return to our theta tunable time to digital converter and add another programmable clock generator. This programmable clock generator acts as the primary input to the clock generator that generates our launch and our capture clock. And this new programmable clock generator defines a relationship phi that is the phase relationship between our synchronous sensor sampling and some victim computation on the board. Now I'll note that phi has always existed. In prior works, it's just been implicitly assumed. What adding this new programmable clock generator allows you to do is explicitly define phi, and as we'll see, exploit it. And so to test this phi tuning, we instantiate our sensor alongside a soft processor that's primed to run AES computation, and both the sensor sampling and the soft processor are running at 25 megahertz. We then rotate this phase relationship phi by 2 periods. First with the processor disabled, and we measure the output of our sensor. We measure how far signals are propagating and how noisy those signals are, or how much information is contained in the power distribution network. Then we do that same process again, except this time with the processor enabled. We again perform the same set of measurements. And from our theoretical intuition, we expected to see a single optimal value of phi, where we optimally line up with our synchronous window of sampling and when the victim computation induces information in the power distribution network. But what we ended up seeing is there were many optimal positions of phi. If we look at the first row here, red is the background sweep. So that's before the processor has been enabled. We saw that there were many positions of phi where we saw higher and lesser load on the power distribution network. Similarly, in the third row here, we're looking at the standard deviation of the output of our sensor, or potentially how much information is contained in the power distribution network. And again, in the background sweep, before the victim computation is enabled, we see values of phi where there is more and less information contained in the power distribution network, not a single optimal point of phi. What's actually happening here is that the background sweep is that the optimal value of phi is blending into the sensor background noise. The sensor itself is inducing information onto the power distribution network, and then it is subsequently capturing the information it itself is inducing onto the power distribution network. And what we can do is we can take the difference between this background sweep that we performed and the sweep performed when the Pico AES, which is our soft processor, was actually activated. And once we do that, in the second and fourth row here, we then see a single peak. And that single peak represents the optimal phi, that is the optimal phase relationship between our synchronous window of sampling and our victim clock. Now, we actually wanted to test both our theta and our phi tuning. So we create a hypothetical cloud FPGA attack. We co-locate our sensor with each of 13 victim computations, and we do this on 5 FPGA boards. We then tune our sensor to some value of theta and phi to either minimize or maximize theta and phi, depending on what we're trying to show. We then sample our sensor as some victim computation is executing. we're going to reserve some number of these boards as a training set, and then some number of boards for testing. And this is going to represent the divide between a local set of boards that you could build a training data set on and an actual attack, which is an FPGA in the cloud that you've never seen before. We're then going to process the data. We begin with a raw time series, which is the output of our sensor. We decompose it into the frequency domain, and then we use that to train and test a very, very simple single layer network, which is then going to give us the probability that our sensor was capturing samples when it was alongside some victim computation. And the classification accuracy, what is the probability that our simple classifier is correctly guessing what application was co-located next to our sensor? The accuracy of that across these 13 applications reflects our sensor's ability to capture sensitive information across this power channel. And this classification attack acts as an important precursor to traditional CPA attacks, for example. You first want to determine that some cryptographic core is running alongside you, then you could perform some key extraction attack. And so what we see in the worst case, where we just minimize the standard deviation of theta, or we pick the theta that gives our sensor the minimum standard deviation. So we're placing that transition on one of those plateaus we saw in the stair stepping. And then we minimize the standard deviation as a function of phi. So we have a phase misalignment between our synchronous sensor sampling and the victim computation. We see a predictably poor 32% classification accuracy. So our classifier is unable to correctly determine what application is running alongside us on the FPGA. When we then improve the theta tuning, so move the transition off one of those plateaus into the carry primitive itself, but we still leave phi minimized, we improve to a 51% classification accuracy. So it improves significantly. When we then just pick the maximum value of theta and phi to maximize the standard deviation of our sensor, so not using that background subtraction technique yet, we get a very strong 75.78% classification accuracy. So we're very accurately able to determine what application is running alongside us on the FPGA, though we are totally logically isolated. Then we perform the same process, but this time we use background subtraction. So we take that sweep before the application is activated, and then that same sweep once the application is activated, take the difference between those two phi sweeps to find the ideal phase relationship between our synchronous sensor sampling and that victim computations clock. And we get a classification accuracy of 75.5% classification accuracy. So why is background subtraction actually making our classifier perform worse? Well, to investigate this, we checked the cross-validation performance. And what I mean by that is we tested every combination of training and testing boards out of a set of 5 FPGAs. And what we saw as we examined the accuracy versus the number of training boards that we used is that background subtraction reduced the interquartile range of the resultant classifiers by 2.3 times. We then did the same thing for the loss versus the number of training boards. And we found that background subtraction reduced the interquartile range by 5.8 times. And so what we're actually seeing is that sensor readings, when background subtraction is used, the data captured from that sensor is generalizing better. We're capturing less artifacts of the FPGA itself and more artifacts of the actual computation. And to put this in a different language, background subtraction is out of distribution generalization. And that is a fundamental quality of any cloud-based attack, where an FPGA in the cloud where you're actually performing the attack is always going to be out of your distribution. In conclusion, don't let theta and phi assume a random value. They can be controlled to dramatically increase the efficacy of your time to digital converter. Thank you very much.
Colin, any questions?
Hello. Is there any feasibility in discovering F from this? Given, I think that your analysis was assuming that everything's running at 25 megahertz, right? Can you recover a frequency if you don't know it beforehand from this methodology?
Yes, you can. That is not the primary focus of our work, but if you just took very long sensor samples and then looked for the dominant frequency out of the fast Fourier transform, then you could determine what the dominant frequency is and what is the frequency of the victim computation. We do assume in those experiments that the victim core is running at the same frequency as our sensor sampling, though we think the first step in using this technique is to match the speed of the sensor sampling with the frequency of the victim computation, which would use a technique like this, a frequency sweep.
Thank you.
Thanks.
Thanks for the talk. I just want to ask because I tried to manipulate the clock phase on the AWS before, but it seems like the Amazon Cloud Service doesn't allow me to manipulate those clocks because all the MMCM are taken by the shell. So I just want to ask, how did you implement this on the AWS?
You were not able to use dynamic phase shifting on AWS? I guess I need to more specifically look at what you did. We've successfully been able to do it. I'd be happy to send you a link to our repository if that helps you figure it out. Sorry, I don't have a more direct answer for that. But it definitely does work on AWS. You can use the MMCM dynamic phase shift.
So how many of the 13 cores were running at a time when you took the measurements?
Only a single core is running at the same time. But we actually see this fee tuning technique as being an important tool if you're running alongside 10 different cores. You can perform a background sweep when you're the only tenant on the FPGA, and then you know what the background looks like. And then theoretically, as long as those 10 other tenants aren't in phase with each other, you would see 10 different peaks in the emergence difference. And then you could tune to a particular peak to focus in on the side channel leakage of a particular application.
Good, thank you.
Thank you.
Hi, I'm wondering if the attacker and the target application using the same clock source, like the same oscillator, they have any if there's any very minor frequency difference, will it affect the accuracy?
Sorry, could you repeat that? Maybe.
Sorry, it's like the if the attacker and the target application use different clock source, will you still able to recover the key, for example? Like they are using different crystal oscillator, so they have small minor frequency different. I think that is possible because like FPGA, it has like a multiple clock input, right? And you can connect to different like a crystal oscillator.
So the question is,
in this case, are you still able to run the stat channel attack? For example, one clock is like 25 megahertz, the other one is 25.00001 megahertz.
I see. So do we require that the speed of the sensor sampling is the same as?
No, do you require the clock source are the same?
Do we require that both the victim and the sensor
using the same clock source
derive? We assume that they do not derive from the same clock source. We assume that there is complete logical separation between the victim computation and our sensor, and that includes clock sources. They may be derived from the same crystal oscillator on the same FPGA.
Yeah, but that means like it's still synchronized, right? Like the two source.
Say that again?
So the two clock sources are still synchronized because they are driving from the same oscillator, right? So I'm just to try to make sure the case, if you are using different like clock source or the same clock source.
We are using the same clock source.
Okay, thank you.
Yes. Sorry, I didn't fully get that originally. Thank you.
Thank you. Very nice talk and very good presentation.
Thank you.
The question I have is, have you looked at your techniques from the point of view of how, if and how these techniques can actually be used to mitigate such attack by the victim, like as opposed to protecting the information?
Yeah, we see our work as sort of a response to the many stopgaps that have emerged to protecting multi-tenant structures. So there's been a lot of interesting work. You know, we could surround these tenants in banks of ring oscillators to try and obfuscate the information that they potentially induce onto the power channels. And we're trying to show here that, you know, you may make it harder, but the abilities of the attacker will continue to improve. And what our sensor allows us to do is really finely isolate what the, you know, where to look for this power side channel leakage. And it seems like the only real solution here is to have multiple power distribution systems on the same FPGA if you're to truly build.
Sure.
secure.
Yeah, I understand. But my point was that phi and theta tuning that you're talking about, can actually the victims employ techniques like that to, let's say, scramble a
I see.
sensor trying to send such information to counterattack such attacks? Have
I
you
see.
thought about applying that to that?
Yeah, so
something to think about.
If the victim computation could be continually phase shifting its own
Precisely,
clock,
something like that.
you
Yeah,
could never get a lock on it with our time.
exactly. That would be an interesting way to see if you can apply that.
Yeah,
technique.
that's a great thought. Thank you. We have not implemented this large set of 13 applications on AWS, but we implemented some DSP operation. It sort of emulates neural network architecture on AWS, and we found that we could capture power leakage across SLRs, but this was a very idealized construction. Though my understanding of the prior work is that there's little issue capturing side channel leakage across SLRs. There's no real power isolation.
With that, we're going to have to move on to the next presentation. Let's thank Colin again.